Okay, hello everyone. Today we're going to learn about series tests. First, what is a series? A series is an infinite number of terms in a sequence, or a sum of them, and we want to use series tests to determine if they're convergent or divergent. Convergent means that the sum will approach a finite number, and if it's divergent, that means the sum will not approach a finite number and it will just go off to infinity. We also have partial sums where this series goes to, it has a certain amount of terms, and an infinite series, which is what we'll usually be dealing with, has an infinite number of terms. And yeah.
So the first test we're going to be looking at is p-series in geometric. So for p-series, you have the equation 1 over np, n to the p, and p has to be greater than 0, otherwise it diverges, but if it's greater than 1, it converges. Now, if p is directly equal to 1, that means it's harmonic and it's also divergent. And in this example right here, you can see it's harmonic, whereas right here, the p is greater than 1, so it converges. Moving over to geometric, the equation is a r to the n. That way, if you plug in 0 for n, the first term would then be 1. Anything to the 0 power is 1, so 1 times a. A is the first term. So it converges when r is greater than 1, and it has to be the absolute value of r. And it diverges when the absolute value of r is greater than or equal to 1. Wait, pause. Yep, pause. So it actually converges when r is less than 1. And the sum equation is a over 1 minus r, which is the first term over 1 minus the ratio given above. Now, an example of this is 3 to the n over 4 to the n. Let me write it bigger over here. Now, you can see they're both to the n power, so you can actually pull that out and you get 3/4 to the n. Now, this looks like a geometric. And you can do a over 1 minus r, so you can plug in, you get 3/4 over 1 minus 3/4. That is if your n is equal to 1. If your n is equal to 0, your first term would be 1, so then it'd be 1 over 1 minus 3/4. This is just basic algebra. 1/4 over 3/4 is equal to 3. This is 1 over 4. Is equal to 4. So these are both greater than 1. 4 is greater than 1. 3 is greater than 1. If you come over here, it shows that they both diverge. They are both greater than 1.
Alright. So now it's the nth term test. Obviously, given a series, really simple. You take the limit as the series approaches infinity. If that does not equal 0, then the series diverges. This test does not prove convergence. It only tests for divergence. For example, if you have this series right here, when you cancel out the powers, you get 2n minus whatever, 2n over 1 basically. You take the limit as as n approaches infinity. You get infinity does not equal 0, that diverges.
Okay, so next test, alternating series test. You have n equals 1 to infinity, -1 in parentheses, n to the minus 1, to the n minus 1, a sub n. Now, you can have it look many different ways. You could also have it look like this, because it's really just -1 to the n times 1 over n factorial. But that all converges if it's greater than 0, if a sub n plus 1 is greater than 0, and if a sub n is greater than that a sub n plus 1. Now, a limit as n goes to infinity, a sub n equals 0, that also converges. Those are the two check marks for it to be convergent. Now, the remainder, absolute value of the remainder has to be less than or equal to a sub n plus 1. Let's go to this first example. Now, you can really just separate this to that as well as that. Now, when doing alternating series, you don't need to worry about this part. You can just cross that out, and you want to check whether this is greater, because you got to do the a sub n plus 1. So you have to see whether this a sub n plus 1, remember, put the factorial on the outside, is greater or less than 1 over n factorial. Now, because it's n plus 1 factorial, this is going to be greater, therefore a sub n is greater than a sub n plus 1, and then this is going to be greater than 0. So that's the first check mark. Now you're looking for when a sub n is equal to 0, for the limit is 1 over n factorial. 1 over n is harmonic, but 1 over n factorial is getting smaller and smaller. It's going down and down and down. So it's getting closer to 0, therefore it converges to 0. So that's the other check mark. Now, these are what it shows decreasing, like we said, and the limit as it goes to 0. Now, for the remainder for the first 4 terms, you have to plug in 4, right? So you have to do absolute value r sub 4 is greater than or equal a sub n plus 1, right? So you look at the a sub n plus 1, so you do 1 over 4 plus 1 factorial, and you can have the negative 1 to the n in there, and the n would just be 4. Now, because 4 is a positive square, then this just cancels, that just becomes 1. That is 5 factorial, and a factorial is 5 times 4 times 3 times 2 times 1. This is 6, this is 24, this is
120.
120. So you'll have, for remainder for the first 4 terms, r sub 4 is equal to 1 over 120.
Okay, next we're going to do the integral test. So in the integral test, we just set the series equal to f of n, and the conditions for this test are that f must be positive, continuous, and decreasing for all x is greater than or equal to 1. And all we do is take the integral from 1 to infinity of f of x, and if we get a finite number, then the series converges, and if this integral diverges, then the series diverges. So our example over here, first we have to check our conditions. So let's set f of x equal to 1 over x plus 2 squared. Now, we need to check our conditions, so f must be positive. Well, we can check that any number we plug into x here is always going to give us a positive number because it's 1 over this number squared. So that's good. Continuous, the only place where this is not continuous is when we plug in negative 2 in here, because then that would be 1 over 0. But since it has to be continuous for only 1 to infinity, it's okay, because any number greater than 1 that we plug in here will always be continuous. And then we have to check if it's decreasing, and we could take the derivative, or we could just check the next term and see if it's less than the previous term. So we could do, let's plug in 1. So this is 1 over 1 plus 2 is 3 squared is 1 over 9. Now let's plug in 2. 1 over 2 plus 2 squared is 1 over 16. This is less than this, which means that the series is decreasing. So all these conditions are met, so now we can do the integral test. So we're just going to take the integral from 1 to infinity of this. So this is a u sub, u n plus 2, or x, du, it's just 1. So really, this is the integral infinity 1 of 1 over u squared. So this is really 1 of u to the negative 2. So if we're going to take the integral, do the power rule, u negative 1, negative from infinity to 1, and this is really negative u is n plus 2 to the negative 1 from infinity to 1. This should be in limit notation if you're doing this integral, I guess. So you would do lim n a 1, just as, you know, just a note, but we're just doing it really quick. So plug in infinity, this is negative, this is just infinity to the negative 1, minus, plug in 1, this is negative 3, negative 1. So you have, really, this is negative 1 over infinity, that's just 0, minus, this is negative 1/3, positive 1/3, so this is 1/3, negative 1/3, positive 1/3, 1 over 3. That's finite and positive, which means this series converges. Okay. Also, for the integral test, you have the remainder, and basically the remainder is just in between the next term, the integral from the next term to infinity, and the integral from this, you know, whatever term to infinity. So let's say, you know, we already solved for this one and we got 1/3 when n is 1. So we can set n equal to 2 for 1 over n plus 2 squared. And we already found the general, we already found the, you know, the integral like without the bounds, which is negative, we can really just say negative 1 over n plus 2. Now just evaluate from infinity to 2. This is negative 1 over infinity is just 0. And you have minus negative 1 over 2 plus 2 is 4, which means this is 0 minus negative 1/4, which is just 1/4. So this remainder is between 1 over 4 and 1 over 3.
I've started.
Okay, so this is the direct comparison test, and the big idea with the direct comparison test is we have a big series and a small series, and if 0 is less than or equal to a sub n is less than or equal to b sub n, and if the series from 1 to infinity of b sub n converges, then the series from 1 to infinity of a sub n converges. And if 0 is less than or equal to, or is less than or equal to b sub n is less than or equal to a sub n, and if the series from 1 to infinity of b sub n diverges, then the series from 1 to infinity of a sub n diverges. Now, that might seem pretty confusing, but the big idea is that if you have the big series diverges, you can think about it like that. So this is the big series, we'll call it b sub n. And this is the small series. You know, we don't know what's going to happen to it. Oh, sorry, hold on. Just keep recording. The big idea is if we have the big series converges, right? We'll call this b sub n. And we have the small series that we compare it to. We think that we'll say it converges because it's like it's smaller than this, so it's never going to go above this, so it converges. That's how you should think about it. And then if you have the small series, we'll call it a sub n, diverges, so it goes up like that. Then the big series, you know, it can't go less than that, so it also will diverge. So here are two examples, and what we want to do is we want to compare them to a known series. So for this example, 1 over 4 plus 3 to the n, we can really think about this, because this 4 isn't significant as it goes to infinity, as 1 over 3 to the n. And this is a geometric series where the ratio is less than 1. Therefore, this series converges. And since this series is bigger than this series must converge by the direct comparison test. Looking at the second one, we have ln n over n. Now, when we want to compare this one, ln n is greater than 1 when n is greater than or equal to 3. So we can compare this to 1 over n. And we know that 1 over n is divergent. And since this smaller series diverges, the bigger series must also diverge. Okay, you're good.
Alright, so the next test we're going to do is a limit comparison test. We're first going to look at the limit of 1 to infinity a sub n and 1 to infinity b sub n. So as a limit as n goes to infinity a sub n over b sub n, the L has to be finite and positive for it to agree. If it's not, it'll disagree. And b sub n, if b sub n converges, then so does a sub n, if it's finite and positive. Now, you can see over here, a sub n over b sub n is equal to L or infinity, and b sub n diverges, then a sub n diverges. So let's get into some examples. So as you have the limit from 1 to infinity, right, you have n squared over n to the 5th plus 8. Now the plus 8 doesn't really matter, so you can just cancel that out. And you're looking at n squared over n to the 5th. You can really just cancel out this n squared, and this 5 becomes a 3. That's where you have 1 over n cubed, and that converges because of p series. If you look up here, limit as n goes to infinity, a sub n over b sub n, which is what we just talked about, and you multiply the flip, so n cubed times this n squared on top is n to the 5th over n to the 5th plus 8. Now, just like earlier, that 8 doesn't matter, and n to the 5th over n to the 5th is 1. Now, because this converges, and that's a finite positive, it agrees, therefore it converges. Now, in the second example, 1 over root n squared plus 2. Really, it's just n to the 1/2 times 2. So that just becomes n. The plus 2 doesn't matter. So it's really just 1 over n. And that's a divergent harmonic. When you multiply 1 over n, and the flip of that, it becomes n over root n squared plus 2. Now that's equal to 1 because it becomes n over n, right? Because it's the n to 2 times 1/2. And that is 1, and because it's finite positive, it agrees with the divergence of that.
Alright, we're going to do the ratio test. So basically, you have a series, take the limit as n goes to infinity of a sub n plus 1 over a sub n. If it's less than 1, the series converges. If it's greater than 1, the series diverges. If it's equal to 1, the test is inconclusive. So here's our example. Alright, so what you want to do is first, this is a sub n. So what we want to do is get a sub n plus 1, which is 2n plus 2, because this 2 is being multiplied by the n, so it's 2n plus 2, right? And same thing with this 5. Like if you factored it out, it'd be 5 times n plus 1 over 5 plus 1, that's n plus 6/5. Multiply the 5 back in, that's 5n plus 6. So that's a sub n plus 1. So if we're going to divide that by a sub n, we can really just multiply that by the flip of a sub n. So what you can do is just do 5n plus 1 over 2n factorial. And now what we want to do is we can really condense this down to 2n plus 2 times 2n plus 1 times 2n factorial. And you know you still have 5n plus 1. That's coming from right there. And then that's all over 5n plus 6 times 2n factorial. Now we see these can cancel. And we're taking the limit of the absolute value of this, but you'll see it's not going to matter too much. But when we take the limit as n goes to infinity here, we use our, when you're taking the limit as n goes to infinity, when the power on top is bigger, it just goes to infinity. And in this case, power up here is basically n to the third. The power down here is just n. So it's just infinity. Now, if we go back to our test, if it's greater than 1, it diverges. And since infinity is greater than 1, this series diverges. Here's another example. So in this case, remember we're going to take the limit, n goes to infinity, of a sub n plus 1 over a sub n. So remember we want to find a sub n plus 1. So first, this 4, we factor it out, n plus 1, and then put it back in by distributing. It's 4n plus 4. And then this, n plus 1, now is n minus 1 factorial. So that's a sub n plus 1, this is a sub n, so what we can do is take the limit as n goes to infinity. This is a sub n plus 1, so we have e to the 4n plus 4 over n minus 1 factorial times the flip of a sub n, which is really dividing by a sub n minus 2 factorial over e to the 4n, right? So now we need to cancel stuff out. So we can rewrite this part as e to the 4n times e to the 4 and times n minus 2 factorial. Put that all over. So what we can do is this is really n minus 1 times n minus 2 factorial, right? And then we also have e to the 4n right here. So what we can do is cross these out, and remember we're taking the limit of all this, and it has the absolute value bars. So now all we have left is just e to the 4th over n minus 1, and still with the limit. And as we take the limit as n goes to infinity here, the power is bigger on the bottom, so that's going to equal 0. And since 0 is less than 1, this series converges by the ratio test. Alright, one more test, root test. Really simple. Just take the limit as n goes to infinity of the nth root of a sub n. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, the test is inconclusive. So here's our example. So all we're going to do is take the limit as n goes to infinity of the nth root of 3 to the n over n to the n. So that means that the n's are all gone. We just have the limit as n goes to infinity of 3 over n. Since the power is bigger on the bottom, the limit equals 0. 0 is less than 1, so this series converges by the root test.